to share with you some result of my PhD thesis, which is about dipole formation at active materials and polymer interface in organic-based photovoltaic. So actually today, I'm not planning to talk about device performance or efficiency or comparing this result with the literature review, because actually this is not our aim in this study, but I will talk about new polymers that used as cathode interface layer and study the fundamental mechanism of the interface structure. So let us start with the interface and have briefly talk about the interface, which is very important to understand the fundamental mechanism of the charge transport over the interface. So here we have actually the common structure of organic photovoltaics, which usually they use zinc oxide as a cathode interface layer and molybdenum oxide as the whole collection. So many studies have been focused on the interface, in studying, I mean, the interface between the zinc oxide and active materials, or between the molybdenum oxide and active layer. So we need actually to know what's happening exactly at the interface between, for example, the zinc oxide and polymer layer. So if we have zinc oxide and put on the top active layer or polymer layer, the first thing, the particle will move between those two layers. So there is actually a possibility for the charge transport, for the, chemical intermixing between those two materials. And there is a chance for chemical reaction could happen between those layers. So also in organic photovoltaics, there is something could happen between two layers at the interface, which is the electronic interaction between two layers. So for example, if we have layer A, which is zinc oxide, and layer B, which is the polymer. So if we put those layers on each other, let me just wait. So if we put those layers on each other, the first thing, the Fermi level need to be aligned. So if the Fermi level aligned, the first thing, the charge will transport between those layers from layer A to layer B. And there is actually definitely the dipole will take place at the interface between those two layers. So, but if the layers is not in the good contact between each other, so there is no chance for the dipole to take place at the interface between those two materials. So many studies actually recently, they focused on organic or polymer cathode interface layer instead of using zinc oxide. And this is actually what I'm doing also in my work. Here actually some polymers that used as cathode interface layer, those polymers have been developed by our collaboration by Dr. Yunus. He synthesized these materials, and we studied with the active layer to see those materials, how those materials could work with the active layer, and to see the energy level and the extracting electron and blocking the hole between those materials and active layer. So here actually the normal or the common structure that we used it in our study, in our work, which is the inverted organic photovoltaics. We use the cathode interface layer and in the top active layer. So we didn't make the full device. We focused actually on just the cathode interface layer and active layer to study the interface between those materials and the energy level position of this cathode interface layer when we apply active layer on the top of this material. So the structure of this polymer P11, actually the original version of this polymer is called NDI. What our collaboration did, they actually just added some anchoring group to this structure here in this side and also in other side. For some reason that for work function modification and also for forming a dipole at the interface. And also we use these materials with active layers, which is TK1 as a donor and N2200 as acceptor layer. So what I did actually in my work, I made a thick layer of P11 and on the top different thickness, different thin layer of TQ1 and N2200 on the top of P11, that ranging from few nano to 10 nano or 7 nano on the top of P11 to see what exactly could happen at the interface when we put those active layer on the cathode interface layer. So actually, because we are working on two polymers, we put the two polymers on each other. There is challenging to establish an intact interface and good interface. So there are many factors should be taken into the account. The first thing, the solvent of the polymer, we should select the suitable solvent of the polymer that can dissolve probably in the polymer and cannot wash the other polymer. And also we have to think about the condition, the best condition of the spin coating that can form a thin layer of active layer on the top of P11, and also the concentration play a significant role on that. So we should change the concentration to achieve the good thickness and achieve the good interface between those two materials. So the first analytical technique that we use it to analyze the sample, we used actually neutral impact collision ion scattering spectroscopy. This technique actually, we use it with the low energy ion scattering that utilize the ion at the surface to determine the concentration depth profile of the elements. And here we can see the typical spectrum of the NICISS that obtained from NICISS. That show different elements with started from the heavier element to the light atomic mass of the elements. So what we can see from NICISS here, the depth profile of the bromine. Bromine actually it's a component on P11. So we have P11 and on the top TQ1. So bromine is a part of P11. So this is the bromine depth profile for all the layers for TQ1 on the top of P11 with the different thickness of TQ1. So what we can see from NICISS, we found actually a shift of the onset of the profile to the large depth, as you can see here, and also there is a change on the distribution of those spectra. And actually, from this shift, we can determine the thickness of the layer of TQ1 with the respect of the bromine that's obtained from the pristine polymer, pristine P11. So, for example, if we have a large shift of the depth profile, which means we have a thick layer on the top of P11. Then, in terms of the chemical analysis, we used XPS to investigate the chemical interaction and also to determine the chemical state of the elements by using the XPS. So the first thing, we have the bromine peak for all the samples, for TQ1 samples and N2200 samples. After putting those samples or putting those layers on the top of P11. So what we found actually, we didn't see any shift, any change on the bromine peak. All the bromine peaks, they have the same binding energy in both, and also they have almost the same intensity, same shape, same spectra. We couldn't see any change, which means actually this is there is no chemical interaction can happen between those layers. But the interesting thing actually is that with the layer of TQ1 and N2200 for the carbon peak, so if we can see here the carbon-carbon for the pristine one is usually sitting at the position of 285 something, but after applying different or after putting different layer of TQ1 on the top of P11, we can see a shift of this peak to the lower binding energy. And this shift, we estimated it was about 0.5 electrovolts. And the same observation was found for N2200 And we can see actually here the carbon peak is shifted also to the lower binding energy, but that happened by increasing the thickness, by increasing too much the thickness of N2200 on the top of P11. So this is actually a minor shift. We found it for N2200, but it was a very obvious shift with the carbon-carbon for TQ1 layer after depositing this layer on P11. Same result actually here was found with the sulfur peak. We found actually the sulfur peak shifted to the lower binding energy. Also after increasing the thickness of TQ1 on the top of P11. And also there is a minor shift of sulfur changing or shifting to the lower binding energy after adding this layer on the top of P11 and increasing the thickness. So to understand exactly what's happening at the interface, we applied also ultraviolet photoelectron spectroscopy and inverse photoemission spectroscopy that to measure the valence band from UPS and conduction band from IPES. So here actually we can see the secondary electron cutoff for the layer TQ1. That used to measure the work function of the materials. And on the right side, we can see the valence band region for TQ1 on the top of P11, and also the conduction band edge that obtained from IPES. So the valence band here for the pristine 1 and pristine TQ1, there is a change. Actually, we found it here for TQ1. If you can see, there is a shift for shift happened for TQ1 pristine 1 on the top of pristine 1 on ITO. So to know exactly what's happening for the valence band spectra, we introduced another method. It's called Singular Value Decomposition algorithm to decompose all the UPS spectra and get references spectra that can present the surface of the samples, and also to get a weighting factor from this UPS spectra, which can tell us the fraction of the surface in which part can form by the respective of the component. So what we found actually from SPD here, from this algorithm, we found actually after using all the UPS spectra, two references. The first component is reference A, which is exactly in the same shape and the same feature of TQ1, but shifted on the energy scale by around 0.7 electrovolt to the lower binding energy. And the second component is P11, and this is can be identified as P11 spectra, and doesn't show any shift on the energy scale. Same observation, we found it for N2200 layer. For N2200, we found also two references. The first reference is exactly same as N2200 spectra, but shifted on the energy scale by around 0.2 electrovolt. And also the P11 spectra, it's similar to the reference Peta or reference P, and doesn't show any shift on the energy scale. So here we can see the obvious shift from TQ1, and we found actually a minor shift for N2200. And actually this is corresponding to the result of XPS, because we found actually in the carbon 1s a major or obvious shift for this for the carbon-carbon to the lower binding energy by around 0.5, and a minor shift for the carbon 1s for N2200 to the lower binding energy. So this result is corresponding to the XPS result and agreement with this result. But the question now, what is the physical meaning of this shift here? The physical meaning actually is assigned to the dipole formation at the interface, that the dipole take place at the interface between TQ1 or N2200 and P11. And because actually we know the shift, it was to the lower binding energy, so that an indication to know the direction of the dipole. So the negative end direct to the TQ1 or N2200 layer, while the positive charge move to the P11 layer, as you can see here on this diagram. So for the weighting factor, we actually found also the weighting factor for the two component A and component B, which is presented the surface of the sample. So we found actually the pristine P11 shows a decrease when we increase the amount of the TQ1 on the top of P11, and also here we can see increase the P11 by increasing the thickness of TQ1. Same observation we found it here for N2200. The pristine P11 decreased by increasing the thickness of P11, and also the N2200 increased by increasing the thickness. It was very obvious and clear for TQ1, and here it wasn't that much clear because maybe this is due to some inhomogeneous layer on the top of P11 for N2200. And to know exactly what's happening on the interface, or to confirm the result of UPS, we applied another method. It's called metal stable impact electron spectroscopy. This actually technique can measure the outermost layer of the surface. And we applied the same method, singular value decomposition, to see how many references we have that can present the surface of the samples, and which reference can be, which reference can be identified from those layers. So after applying the singular value decomposition, we found actually also two references, reference A and reference B. So the reference A is similar to the TQ1, but also shifted to the lower binding energy by around 0.5 electrovolt. And the second reference is similar to P11, but doesn't show any shift on the energy scale. Also for N2200, we found two references. One is identical as N2200, and the second one is same as P11, but doesn't show any shift on the energy scale in both for N2200 and for P11. And actually that makes sense because in the fact of the MIES, the MIES actually is sensitive for just the outermost layer, but UPS can be probing deeper on the depth by around 2 or 3 nano. So now here the energy level for all the samples for the individual TQ1 and N2200 and P11, and we want to know how the dipole work at the interface. We know from the result of UPS there is a dipole take place at the interface between TQ1 and P11 and between N2200 and P11, and all these values here actually were obtained from the electron spectroscopy. So the question, how the dipole work at the interface. Here we have all the layers together. So due to the dipole that formed at the interface, we can see actually the HOMO energy level and LOMO energy level in both in TQ1 and N2200 shifted upward by around 0.7 electrovolt and 0.2 electrovolt in N2200. So as a result of this shift, the position of the HOMO level now is far from the position of HOMO of P11. So in this case, the hole can be blocking from TQ1 to P11, and this is what this is a favorable, and this is what we want because TQ1 actually it's working as a hole blocking. On the other hand, we can see the LOMO of of N2200 is affected a bit by the dipole formation and moved above the LOMO of P11. So in this case, the electron now can transfer easily from N2200 to P11. And also this is what we want from this layer, because N2200 it's work as acceptor layer. So in this case, the energy level alignment meets the expectation of using P11 as cathode interface layer for blocking the hole and facilitating the electron when we use TQ1 and N2200 as active layer in this device. So in conclusion, we had actually a range of the thickness of TQ1 and 2200 on the top of P11, and we ran a combination of the method to determine the chemical intermixing and also to study the chemical state between the interfaces. From NICISS, actually, we determined the concentration depth profile across the interface. And from UPS, we found actually the spectra of TQ1 and N2200 shifted to the lower binding energy by about 0.7 electrovolt for TQ1 and 0.2 electrovolt for N2200. So the physical meaning on the end of this shift is related to the dipole formation at the interface between those layers, between TQ1 and N2200, or P11, I mean, or N2200 and P11. So the energy level meets the expectation of using P11 as interface layer for blocking the whole transport. So this layer, this interface can be used in organic photovoltaic device. In the end, I would like actually to thank my supervisors, Gunther Anderson and Matt Anderson. And also I would like to thank Dr. Jonas, who provided these materials to use it in our study. Thanks a lot.
Thank you very much. We can open up for questions from the audience. So please, if you would like to ask a question, you just need to unmute your microphone first. Does anyone have any questions for Amira? Nathan, I see you've put your hand up. Please go ahead.
Hi, Amira. Thanks for the talk. Congratulations on finishing your PhD.
Thank you.
I had a couple questions. The first one, as a result of your experimentation, do you have any idea of how to mitigate those that interface mixing when using polymers as the cathode interface layer?
Do you mean how I know if those layers intermixing or no?
No, not so much, because obviously, like your results have shown that you do get that sort of that dipole production at that interface layer. So there must be some sort of intermixing going on. I guess my question is more, did you have any thoughts as to how that could be prevented if you were to use, say, one of these polymers as that interface layer?
No, actually, just I tried those layers with different conditions to optimize the interface between them. It was in the beginning, it's very hard to optimize this interface. So I tried to change the solvent, so change the spin coating, the concentration, until I reached to the good interface between them. And from seeing this or chemical intermixing, I used XPS and see that chemical intermixing on those layers. Okay, cool. Yeah, I suppose there's really not much to do unless you do further experimentation to see whether or not you can reduce that amount of intermixing. But my second question was, how do these polymers compare to, say, like using, because you established that zinc oxide is normally used as that interface layer. How do these polymers compare in terms of, say, producing a more efficient cell? Actually, I didn't try it with those polymers still. This is the next step I have to do it in the future, to use zinc oxide and compare it. First, I have to do a full cell of those polymers and study the efficiency. And then in the end, I have to prepare the control device, which is a zinc oxide, and then compare the results with each other. Yeah, of course. All right. Exciting. But yeah, that should be an interesting result. Yeah, thank you so much. Thank you. Thanks.
We would have time. One more question. Gunther, I see you've unmuted your microphone.
Yeah, the question actually for Nathan. So it's the so why would the avoiding the intermixing be actually important?
Well, I think as Amira was talking about, it acts as a whole blocking layer, doesn't it? It reduces the amount of electron holes that can actually be transferred to that electrode, if I'm understanding it correctly. Is that correct?
Yes,
Yep.
but so my question basically is, so if you do that at a sharp interface, or if you do that over, let's say, a layer thickness of a few nanometer or so, it's a question out of curiosity, basically only. Would that make a difference for the functioning of the device?
I can't presume to know the answer to that,
Yeah.
unfortunately. I guess that's an area that
Yeah.
needs to be tested.
Okay.
But that
right.
is a good point. Thanks for that.
Yeah. Okay. So I guess we are running out of time, so we will have to leave it there. Everyone, please join me in thanking Amira one more time for the interesting presentation, and it's good to hear some discussions going on about the implications of that. So Amira, yeah, thank you. Please stop sharing. Yes, excellent. So our next